hypothetically speaking, even if I have solutions right in front of me and I just have to even copy that, let's say 6-7 questions take a considerable time, and if I, without seeing any solutions, if I want to try, oh, definitely it will take quite a bit of my time. But my whole point is that this is a 3 credit hour course, and if there are 7 days in a week and I am giving you 4 to 5 or 6 problems, that's one problem a day. That's around 2 to 3 hours or 2 hours of hard work outside the classroom, right? So for a 3 credit hour course, how much time you need to spend outside? There was this rule of thumb, at least 3 hours, but definitely more than 3 hours if you ask me. So we will be doing a couple of more problems related to static indeterminacy, but right now I definitely want to touch this. And then if we have time today, I will go back to our usual, there is this structure. We are putting a load. There is a, let's say, a wire, deflection happens, change in length in that wire happens. We will go back to our usual stuff. Okay. Good morning. How are you? Okay. Hello. Good to see you. Good morning. Okay. We have how many students? Hello. Hello. Are you good right now? Good. Good to see you. Hello. Okay. Okay, we are touching 1038. And 38. Great. Then 39. Hello, good morning. Hi. Okay, so we are starting in 10, 9, 5, 4, 3, 2, 1. Okay, everyone, welcome to another 206 session. Okay, I did post another homework. You might have observed that yesterday. Not sure. You may want to have a quick look at that homework. Solutions for first 2 homework have already been posted. One of the students just reminded me that I did mention this, that I would be uploading the fall 2021 midterm exam one for you as well. So you can just yourself solve it and just have an idea where do you stand in terms of your progress. There is one topic in that midterm one that we haven't covered yet, but I will be uploading that midterm one. You can wait for few more days to solve it if you want to. Midterm exam dates will be announced by me via an announcement. You have to give me at least 1 day, please, 1 or 2 days. Do you have any questions for me? Any questions, concerns, reservations? No? Okay. So do you see that, fellow? I have this structure. I hope our online students can also hear me, and I have already shared the screen. So everyone can see that I have this nice and beautiful fellow. In fact, I will test the mic just one more time. Okay, okay. Okay, yes. So I have this structure, you can see, right? Now this structure, oh, come on. Yeah, this structure is subjected to this load, right? P equal to P prime. Now this load can be like this as well, doesn't matter. The point I'm trying to make is that if I make a nice and beautiful cut from here, and I start to observe the stress distribution, I immediately realized that till now in this course, I kept on telling you that you need to, that we have these nice and beautiful arrows. Well, that doesn't happen actually. You can see that you are observing a little curve like this. And you can see that I made this cut at exactly the dimension of B. Now, why don't you focus on this fellow here? What I do is that now I make a cut right through here. I make a cut and now the stress distribution is like this. Now this is again a little bizarre, right? Because I have been telling you stress is equal to force per unit area. And when I used to tell you this, we all used to picture a nice and beautiful rectangles in our heads. And you used to think that stress is equal to, average stress is equal to P by A. Great. But right now, when I'm looking at the stress distribution, that I'm feeling a little worried. The worry I have is that I have this as my average stress. Why don't you have a quick look at this dashed line? This is my average stress. Let's say I have designed a structure for average stress. Now what happens is that there is this individual stress line that goes way beyond this line, right? This means my structure can actually fail. The story. So this average stress is this rectangle line. Can everyone see this dash line? Our online student, our in-class student. This one, this dash line, this dash line, this one, this dash line, this one. This is the average stress that you have been talking about. Okay. Now this weird behavior keeps on continuing. This time I make a cut at 0.25 the width of this object. The moment I make a cut, I'm shocked to see that the stress lines are like this. And the crazy part is that again, if I ask you, give me the average stress, you will say it is equal to P by A. So I am telling you that the average stress is equal to this. And even if I design the structure that remains within the limit of P by A, and I'm feeling very confident and happy that the structure will not fail, the structure will fail because the individual line, you can see, individual line goes way beyond this line that you drew. So this means that I need to be a little careful. When? Well, I need to be careful when I'm talking about this portion, this portion, this portion, this portion, this portion. In fact, even right now, you see, I should be a little careful even till here because, well, sorry for that. Let me switch off this. Yes. So I need to be very careful. Now, you may want to ask, what about this minimum stress? Well, it says that this little line is 0.973 of the average stress. And I told you that the average stress line is like somewhere like this, let's say. Hang on. Somewhere, probably a little bit here. Let me draw again one last time. Somewhere. Yes, now I drew it correctly. What is stress max? I'm talking about this line. It is equal to 1.027 times stress average. Okay, why don't we talk about this fellow now? You can see that the stress max, that is this line, is equal to 1.387 times your average stress. And this minimum line, this little line, is around 67% of your average stress. So I think you understand my point. But here, this goes ridiculous. Maximum stress is 2.6 times your average stress. Now, all of you have one quick question in your minds, right? That question is, what happens here? Right? Because I never drew this, right? So can anyone tell me what would happen if I make a cut here? It will be pretty much the nice, beautiful rectangle I have been telling you in this course. Okay, what if I make a cut here? The same behavior as this starts to appear, because again, you're near to the load. What happens if I make a cut here? Yeah, of course, this behavior, because again, you are very near to the load. And what happens if I make a cut? Hang on, like here. Again, this behavior starts to appear. This means you cannot just, every stress is equal to P by A and finish the story. No. You're talking about that when you are way away from the point of application of load. This story was told to us by this gentleman, Saint Venant, back in the 1700s. Sorry? Yes.
That's the French pronunciation.
Yes, French pronunciation. Yeah, which I am not very good at. Saint Venant. Did I say it right? Almost. Okay. Anyways, so this gentleman told us this story that if you're talking about average stress is equal to P by A, all of this story is true when you are way away from the point of application of load. In fact, I will also comment that as long as so you don't need to worry, we will immediately go for a problem as long as you are or we are away from force, point of application of force, or change of material, change of area or material. As long as we are away, life is good. Average stress is equal to P by A. Average stress is equal to P by A. Life is beautiful. So far, so good. Easy, right? Section. Okay, it's in fourth chapter and second chapter. I will cut those pages and I will post as well. So you are not asking me any question, which is not good. Let me scroll down. Oh, yeah, you can take a picture. Okay. 7, 6, 5, 4, 3, 2, 1. Okay. Okay, let's talk about this. Do you see this? Now you see that there is this hole, this fellow, right? So you can make this like this. This is a nice and beautiful rectangular chunk, rectangular piece. And I asked you, why don't you give me stresses? You said that's so easy. Average stress is equal to P by A. Not so fast. The problem is that you have made a hole here. Now, essentially what happens is that if you make a cut here and cut here, you thought I will just do P by A. The problem is that, do you see this black line, this one, everyone? Huh? This is what you predict. But actually what happens is that the stress lines are behaving like this. They are non-linear. And if you design the system for this and you're feeling very happy, the structure will still fail. You know why? Because of the fact that actually the stress is way higher than what you were predicting. So again, if you're talking about a structure with a hole, you need to be careful. So your immediate question will be, so why don't you tell us what will be the stress then? If this gives me a wrong estimate, what should I do when I'm talking about stress in this zone? We will talk about that in the next 5 minutes. Okay, let me show you one more diagram. 7, 6, 5, 4, 3, 2, 1. Again from your textbook. Boom. Do you see this? You have a nice and beautiful object. Again, this is rectangular if you want to make a nice and beautiful diagram on your pages. Nice, beautiful. You can color it as well. Now, an interesting thing that you see is that now if you draw a cut, not here, not here, not here. If you draw a cut right here, now all of you will say that this cut is far away from the point of application of load, right? It is far away. But do you see that this cut is very close to this, right? The change in area. So if you make a nice and beautiful cut here, and you see, then you will see that the stress lines have this nonlinear profile. And even if you were predicting that the average stress at this section will be P by A, and were feeling very happy, your structure can technically fail because you did not know that this is predicting only this stress, where you have actually individual stress line that exceeds that prediction. Are you following me? Sure. Okay, good. Do I have any more diagrams for you, by the way? Oh, I don't. That's not good. Okay. So this is not good. No more diagrams for you. Give me 1 second, please. Let me make one more. I really want to add one more nice story to the picture, and that is, hang on for a second. Okay, anyways. Okay, now what is the answer to all of this? Let me zoom in a little bit. The answer is K equal to stress max over stress average. This is our stress concentration factor. In fact, I'm using the word concentration. Why don't I try to tell you one thing? 6, 5, 4, 3, 2, 1. You need to give me 1 minute. So you can assume it like this, that you had nice and beautiful stress lines, stress flow lines, if you want to call it, and all of them squeezed in through this little space. So they are being concentrated through that little area. Hence the term stress concentration factor. So let me tell you how would we proceed. What we will do is we will be using some already present charts that are present in our textbooks. Now, usually such kind of charts are empirical, that is experimental. You have a flat bar like this, and you have a hole here, and you are putting a load here. What you will be doing is that you will be using the same formula. K is equal to stress max over stress average. Stress average, you already know. You have been doing the drill for the last 3 weeks. Average stress is equal to force per unit area. That's the easy part. But now we cannot proceed any further because you actually don't know how the individual stress lines are behaving as they are going past or going close to that hole, right? So empirically, you have this nice and beautiful plot. You will open this.
Is this CNG electronic?
No. Okay. So what was I saying? empirically, you have this line. This is what you will be doing. You will open the required chart. You will look at this 2r over d, right? You have radius of the hole. You have dia of, I'm sorry, d means this dimension. I apologize. You will substitute here. You will arrive at a particular, let's say, value. Then you will arrive at this particular value. You will go vertical and it will cut here. You will get a particular value of k, and then you will take this k and you will substitute here. So you can think it like this. Hang on. You have this flat plate and you have a wooden object that goes right through it. And I am holding that wooden piece and I'm pulling this object. Are you getting my point? So I have this wooden piece, let's say, that this is my rectangular structure. This is the hole. Somebody placed a wooden piece through it, and now I'm pulling it. So now the fact that this wooden piece goes through the hole and you have a hole in the structure, that adds to the picture of this stress story. So I have to be using this drawing. I will be doing an example. You just give me a few more seconds. Similarly, you have another of these diagrams. Hang on. Yeah, this one. This one is again for an object in which you have area that is changing. Now, there are many students who are saying, what about this fillet radius? Why fillet radius? Well, we know this from our experience from our childhood, that if you have, let's say, a piece of paper like this with a sharp corner, you just use a little force and it will immediately tear apart. But if you have a nice and beautiful radius to the same piece of paper, you will definitely need a little more force. So this fillet radius actually adds to the complete picture. You will find r over d, you will get your particular value, then you will have a capital D over D, this capital D over small d. Let's say you have a value of, I don't know, 1.5 probably. So you will follow the second curve and you will arrive here. Then you will go horizontal. It will give you a beautiful value of K. You will substitute here. This you already know, and you will calculate stress max. So this will be the procedure we will be following in this class. I will be making an example. If you have any questions, you need to stop me now. Sure. If I'm close to the point of application of load, I need to be careful. Individual stress line will be higher than the average that I used to talk about. If there is an area that is changing, I need to be careful. The individual stress line will be higher than the average stress that I used to talk about. If the material is changing, I have to be careful. Okay, what about our online students? Yeah.
Does the stress is vector quantity or scalar quantity?
Well, stress is actually a tensor. Stress is a tensor, right? We had that matrix. And I think I told you that we use this, but researchers, you should use tau as well if you want to, but this is shear stress. Stress is a tensor. But you can continue with your question actually. So what's the point that you're trying to make?
Yeah, I'm trying to say that you said the stress lines.
Stress flow lines actually.
Stress lines going towards the small d area.
Stress flow lines. I use the word stress flow line.
Does it looks like a force? Like force is a vector quantity, and the pressure is a scalar quantity. So stress.
No, actually,
in which part of this quantity?
I use that sentence that, you know, stress flow lines have to just make their way through that little area. So that was the statement I was making, that these are more like stress flow lines, more like, not the best example, more like water making its way through a smaller area. So these are stress flow lines that have to make their way through that small area.
Modeling.
Huh?
It's like modeling.
It's more like analogy at this point for me. I was coming up with this analogy that it's like a lot of stress flow lines are actually making their way through that little area. But if you want to have a physical perspective of how this is happening, then what you will do is that you have a structure, you take a little cube out of that, you draw that beautiful cube, then you start playing that same game that we used to play a couple of weeks back. We had outward arrow here, these arrows, and then we go through that.
Okay.
Yeah, I'm not sure if I explain it perfectly, but yeah. We can talk about that more, but for me, it's more like stress lines are making their way through that. Okay, 6, 5, 4, 3, 2, 1. This problem definitely you are doing. Now you would be like, why the first example problem we would be doing? Well, because it's very easy, and something tells me that all of you will be able to do it. I have a strong feeling. Okay, you see, nice and beautiful fellow that I created. Yes, no. Okay, and boom, we have this dimension. Then we have this dimension. For those of you who have their tablets or computers with me, let's say our online students, they can be using their textbooks to solve this problem as well, because you will be needing some charts. So I will be opening those charts for you as well.
Are they involved in the book?
Oh, these charts are available in the book. I actually copied them from Bear Johnston. In fact, I can show you right now as well after a few minutes. Okay, the question says that this, yes, no, this nice dimension is 40 millimeter. Beautiful. Okay, life is good. This dimension is 60 millimeter. And you're definitely doing it. And this dimension is 8 millimeter. Nice. The radius. The question says that I have a load that is being applied in this direction, P. Of course, my statics tells me that, of course, you are holding it from here or putting a load, whatever. So this should be P. The question goes and says that you have a depth of 10 millimeter. Wow, 10 millimeter. Right, wrong? How many agree? How many disagree? The question says that you have to tell me. Okay, now I think I have to redraw. I think the load is being applied here. This is a 3-dimensional drawing. Define, okay. Given that the allowable stress is 165 megapascals, you need to tell me P. Okay, hang on for a second. Given the allowable stress is 165 megapascals, then you have to give me the P, the load. Now you have to be a little careful now, because the cross-sectional area has changed, right? So you remember those individual stress flow lines? They are the ones that I am worried about. They might exceed that 165 megapascal and your structure might fail. Wow. So what is the first step if this question shows up in your exam? I will write K equal to stress max over stress average. Second step, stress average equal to P by area. And by the way, I have to be a little careful. Please don't lose sight of the fact that what is this dimension? 10, right? Are you getting my point? Just because I did not draw does not mean that it's not there. So it's like 10 millimeter, 10 millimeter. Third, give me the K from the chart. 4, give me the stress max. Okay, you can take 60 seconds. Just take a picture of this as soon as possible so that I open the paint chart and everyone of our online students and in class can. I think right now you are all at point number 2 probably. So everyone has this picture. Should I go to the paint? Huh? Sure. Positive. Everyone? Okay. 6, 5, 4, 2. Okay. 6, 5. What about our online students? Paint. Okay. Which I think this serves fine, right? Does it? I think it does. Okay, I will go back actually. 6, 5, 4, 3, 2, 1. First thing is, why don't you tell me average stress? Anyone who found the value? Did I give you the value of P? Oh, sorry. Okay. So it is P divided by, so what is the area? Exactly. So you have to tell me which area.
Allowable stress means what?
Allowable? So allowable stress is equal to 165 megapascal means that if the allowable stress exceeds 165, then the structure can get into danger. And for me, this allowable also holds true for the individual stress line. So if there is one line that is exceeding 165 megapascal, doesn't matter.
So that's basically maximum stress, right?
Exactly. So my maximum line should not cross 165.
So the average will be allowable stress, right?
Average stress?
Because we are talking about.
No, I will tell you. I will tell you. So I will tell you about this. So I will have average stress is equal to P by A. And this is equal to stress max over K, right? Okay. Now the area is, what is area? Area will be this one, 10 millimeter by 40 millimeter. So I have stress average is equal to P by A with area equal to 40 into 10 power minus 3 into 10 power minus 3. Now there are students who are saying, why did you select 40 millimeter by 10 millimeter and not 60 millimeter by 10 millimeter? Because this area is smaller. If I have to select between the two areas, I will definitely go for the smaller area. If you go for the larger area, then the stress in any case comes out to be less. So please remember that if you come up with a question in which you have this fellow that is happening, sudden change in area is happening, stress concentration K, then if you have to predict the average stress, go for the smaller area, not for the bigger area.
So I mean, it depends on where you cut, where you imagine you cut.
Okay, I will answer this question. His question is, doesn't it depend on where do you make the cut? The point is that wherever you make the cut. So for example, right now, if I remember correctly, did I even tell you? Okay, right now you make a cut here or you make a cut here. Either way, you are very close to this fellow, right? What I'm saying is, if you are close to this fellow and you want to find the stress concentration factor, if you are talking about the average stress, doesn't matter, as long as you're close to this. If you have to find the average stress and have to use stress concentration factor, go for the smaller area, not the bigger area. Otherwise, it will kill the purpose of the analysis. I have to be safe in making the structure. Now I will find the K. So in order to find the K, I will go back and I will see what does it say. It says R over D, R over D. The R is the fillet radius and the D is the width of this little fellow. So give me the R over D. R over D is, somebody already did that, 8 into 10 power minus 3 meter over smaller dimension is 40 into 10 power minus 3. You said 0.2? Seems correct to me. Let's see. Okay, then I will go back 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The next thing that I need to know is capital D over small d. This is capital D, this is small d. So I will go back and I will do a capital D over small d. Capital D over small d is, I forgot, 60 over 40. Okay, that gives me 1.5. Now for 0.2 and 1.5, I'm stopping here so our students can catch up. Six, 5, 4, 3, 2, 1, 0.2 and 1.5. Okay, just remember these things. Okay, so 0.2, I will open this blue line, 0.2, R over D was that, right? So here goes the shift, nice and beautiful. Then 1.5, this line is my 1.5. Oh, come on. You already did that? 1.5, 1.5. Sorry, yes, this one, 1.5, 1.5, 1.5, 1.5, hang on. Now I will make a cut here. Yes, no, this is the yellow spot. Then I will go from here and I will make a purple line. Boom. What did you say? 1.8? Oh, I think I made a mistake. Why do I have 1.73 in my notes then? Well, that's not good. I don't know why. 1.73. Did I make a mistake? 1. We have to, okay, I have made a mistake, let's say. Let's go back. That's not good. 60 over 40 is 1.5. R over H is 0.2. R over D is 0.2. So 1.5 and 0.2. Let's do it one more time. This is 0.2. This is 1.5. Probably my notes are wrong then. I don't know. Anyways, 1.82 we decided. You have to go with it then. That's not good. Anyways, so 1.8. Okay, now the last piece of the puzzle is stress max. It comes out to, okay, so 1.82. Now I will find my P equal to stress max multiply by area. Yes, stress allowable is stress max. One of the students asked me this question. He was right. Divided by K. And P comes out to be 165. Thank you. Someone was right actually. I don't think I that time said a yes, you were right. Multiply by area divided by K. K is 1.82. Area, I think we decided.
Then also we need to multiply it in area 40 times.
Yes, 40 times exactly. So it will be 40 times 10 multiplied by 10 millimeter square. Give me the value of P, by the way. So instead of millimeter square, I will put 10 power minus 6. Give me the P value.
36.3 kilometers.
Okay, 36.3 kilonewtons. And our answers are, of course, off from my notes a little bit. 36.3 kilonewton. So let me write the comment of one of the students. Stress allowable in this problem is your stress max, as one of the students already mentioned in the beginning. Thank you. Okay, left and right, but we are able to solve this. Yes. We have a question. Yes.
So stress max is like the
Stress max is the individual stress line that goes way beyond the average stress that I have been predicting by using that simple, that average stress is because the individual stress lines are just equally are equal in magnitude, which is completely wrong. Because for this structure, the maximum stress is like this, 6, 5, 4, 3, 2, 1. Please give me 1 second. We have a question. I showed you this one. Where is it? Sorry.
right.
Yeah, this one. So this is your stress max, this line. Right? And that's why this is also my allowable. If I keep this thing as my allowable, then my structure will fail because this is not allowable. This is the allowable. Okay, we're stopping here for 30 seconds. Just is it clear? Yes.
So the graph example for the K, does it always vary depending on the object that we're studying on?
Okay, so what about the graphs? Well, the graphs are different for different geometries. If you have a rectangular plate with a hole, you have a certain empirical plot for that. If you have an object like this that has a variation in this width like that, you have a certain plot. If you have a completely different kind of a formation, let's say, let me give you an example, two holes that are very close to each other. I'm just coming up with an example myself. Then you definitely need experimental result for that one as well. But these are some generally used plates and structures that you observe in your daily life. As I told you, have a plate, have a hole, put a wooden stick through it and try to pull it. Of course, the structure can fail because you are pulling it right through that hole using that wooden stick. So you will be using that other plot that I showed you. Okay, on that note, Baran, Dogukan, Sarchan, Uze, Yasmin, Aisha, should I proceed? No, yes? Okay. Not sure. Any online student who wants to comment? Should I proceed? Is it clear? No? Okay. Okay, 6, 5, 4, 3, 2, 1. You will see a homework on this one as well. So why don't you do this problem? By the way, last time I gave you that one problem. Did you do that problem? Did you do that? No. Okay, we can. Okay, I can give you the answer for that one. I need to actually see that problem. So let me share the screen. That problem was, we already are past 11:20 now. Time just, okay. Okay, when was that class? 24, 23, I think. 23. Okay. Yeah, this was the problem. Did anyone do that? Okay, so the answer for weight is 112 pound. So should we do this problem? I think we should. So let me go for more. There's tools. How do we take a picture? Okay. Okay, let me do it, please. I gave you this problem. I wanted you to do this. Copy selected graphic. Okay, so let's do this quickly. So the first thing I will do in this problem is that I have to screen. Okay, so the first step will be change in ED equal to P L. Oh, sorry for that. P L over EA. Elastic modulus is given to me. The area is given to me for this. Now, the change in length. Okay. Did they give me delta ED? Yes, they did. So from here, I will have 0.0417 inches equal to FED. LED is given to me as, give me the dimension quickly. LED is 8 feet. Multiply by 12 inches divided by elastic modulus is 29 into 10 power 3 KSI into the area is given to me as 0.002 inch square. So students who don't like this, they need to take a decision quickly. So we have inch.
Double prime means
Inches. And 1 prime means feet. Yes, very good. So give me FED quickly. By the way, you should have tried this. You did not? Anyways, that's not good. Sorry. FED is anyone who is using, okay, he's using how much?
0.025.
Sorry, it is 3 feet. It is not 8 feet. Did I give you 8 feet in the problem statement?
Yes.
Okay, so the problem.
Is from B to A.
Huh?
You gain 3 feet from B to A.
Okay, this is not 8 feet. Sorry, guys. This means the problem had been different. That had been given to you. Anyways, if you did go with the wrong statement, even that's fine. This is actually 3 feet as well. My bad. And this one is 3 feet. Why don't you give me the new change in 0.067?
So we need to convert the young modulus as well.
No, that is in kilo pound per square inch. It's also in inches. So 29 into 10 power 3. Yeah, so this thing is in kilo. So my answer will be also in kilo pounds. Okay, got it. Now the second step is that you have to find, I already explained the problem last time, that you have to find how much this mass drops. So it will be tan theta equal to perpendicular over base. And now my base is 5 feet. In inches, it will be this fellow, which is equal to 0.025 inches, right? Which is my 0.025 inches, because in the question statement, I already told you that delta YB was 0.025 inches. .025 inches. I think this was given. Okay, I think we will have to do this problem next time. It's okay. Let me open what was the problem that I gave you? Hang on. Okay, this was given and I have to find, okay, sorry, you are right actually. We have to use the similar triangles first. So this is unknown. Okay, this is unknown. Delta ED you have found, which is equal to 0.0417. And this one is 5 divided by 12. So 5 multiplied by 12. It is equal to, now I will be using the similar triangles, perpendicular over base. Now this is what is unknown to me, how much it drops, delta YB, how much it drops, okay, divided by 3 feet. Clear? Okay, now I will have this ratio. Why don't you give me delta YB, please? .025. Thank you. So this is in inches, 0.0 inches. Now that I have got this, the question says how much this mass drops. So tell me how much this mass drops. Anyone? This plus, yeah, good. This plus total drop equal to this plus the change in length that happens in this metallic rod itself, which will be delta BC. So it will be equal to 0.025 inches plus P L over E A. So tell me the answer. What is PL over EA? Plus 0.025? Yeah, we need to find, thank you. Now we need to find the weight. You cannot proceed in this problem. Very nice. So thank you. So what I will be doing is I will be making a free body diagram Okay. What happened? You can ask me. Okay, so this is my complete rod. This is my FED. Hang in there with me, please. FED. And this is my weight that is acting. And this is the AX. And let's say I am using the vertical for AY. And the question is done. All you have to do is do summation of moments. So you will come up with, let's say, minus FED into 5 feet into 12 inches, plus the weight is unknown, into 3 feet into 12 inches equal to 0. So my W comes out to be minus 3 into 12 divided by minus F, not DD, it's DE, by the way. DE. Okay, this one will become FDE. So give me the value. Do we know FDE, by the way? Sure.
Yes, the tension.
So W comes out to be this one, right? So it comes out to be this one is W is equal to minus 3 into 12. Oh, sorry. Oh, sorry. I think I wanted to say 5 divided by. I'm taking more time on this one, by the way. Why don't you tell me? Yeah, thank you. It will be 5. Okay, FDE multiply by 5 divided by 3. So W comes out to be 0.067 kilopounds multiplied by 5 divided by 3. So what is the W? In pounds, give me in pounds, multiply with 1,000. 112 pound force. LB, you are allowed to put a small f here for pound force if you want. One of the students gave us W value, so I will substitute here with the dark blue color that it is 0.025 inches plus weight is PBC. So it will be 112 multiplied by length is how much? 4 feet multiplied by 12. Elastic modulus is 29 into 10 power 3 into 10 power 3 in kilopound per square inch. Okay, you can actually multiply with 1,000 if you want. Okay, what about area? Area is given to me as what is the value? 0.002. So it will be 0.002 inch square. So everything is in simple terms. Nothing is in kilo. So what is the total drop? Point 0.118 inch. So 112 into 4 into 12 divided by 29 into 10 power 3 into 10 power 3 into 0.002. Okay. Did you do this problem the same way? Did anyone? No? Anyone who did the problem the same way?
I did the problem, sir, but the answer was not right because the code.
Because the dimension was wrong. Okay, that's fine. Bye bye. Thank you. Yes, we really went left and right in this problem. Yes.
I have a question about the diagram. So firstly, we are trying to find delta y at B.
I will tell you what happens is I will tell you.
It goes like this,
I will tell you.
and after that, the cable also in tension. So
No, I will tell you. I understand your question. The whole thing is that first of all, this mass is not attached to this one initially. So you have this cable and you have a flat red rod. Life is good. Then what you did is you hung this mass with this rod, right? The moment you did that, because of this load, this rod goes like this. So this rod has now arrived here, and we are like, okay, because of hanging this load. The question is how much this mass drops. Now the point is that this mass, when it has made sure that this rod arrives here, this mass itself does not stop because it itself has this wire with which this is hanging. So this wire also extends.
Yes.
So nothing happens to this blue line now. It's just this that this mass falls a little more under the fact that this wire is also stretching. But nothing happens to this fellow. Because if you see, this point is attached, for this mass, this point is attached to this. So it falls, it comes here, but this mass continues its
and
journey.
also, yeah.
You get my point? It also stretches, the wire itself also stretches with which the mass is hanging. Because there is a PL over EA in that wire as well. Okay, I have to actually stop this recording because, okay, everyone. Thank you and bye-bye.